Welcome, everybody. Today is week 6, day 1, and this is our final week of this summer workshop on quantum physics for everyone. So far, we've discussed a lot about superposition of quantum states for single quantum objects like photons and electrons. And we saw demonstrations from Henning at Q-tools demonstrating that you can create pairs of photons which are in a quantum state such that we were able to violate the Bell inequalities. And so today I'm going to review that, and then I'm going to go through the representation, graphical representation of entangled states. And if we have time at the end, I'll begin an introduction to quantum teleportation, which uses entangled states. So as usual, if you have questions, type them in the chat window. So to review, remember that in classical physics, if we have any data set, and Alice has two variables called W and X, and Bob has two other variables called Y and Z. Remember that under these assumptions, which are considered to be common sense, logical assumptions in most people's view of the world, which are inherent properties or instructions for each particle, which do not change after the particles are created in the source and travel off to their respective measurement laboratories. And then assuming that the measurement laboratories use fair sampling of measurement settings, and that there's no hidden conspiracies or rigging or faster than speed of light communication, and so on, then we proved very simply, with very simple mathematics, that the average of Q, if you make thousands of measurements under fair sampling, the average cannot be greater than 2. And this has nothing to do with quantum theory or quantum physics. It's purely classical logic that leads us to that conclusion. Okay, so then we applied this classical reasoning to measurements of photon polarization, where Alice is measuring her photon in either the HV scheme, and plus or minus 1 is called W, and then or she can measure in the diagonal, anti-diagonal polarization scheme, and she measures a variable called X. Bob can do the same choices in HV called Y or DA called Z. And in particular, Bob can also rotate his HV and DA analyzing system by 22.5 degrees to get even a more interesting result. But under any definition of Bob and Alice's polarization measurements, no matter how they define their schemes, if you take these classical assumptions to be valid, average of Q cannot be greater than 2. Okay, so then the experiment was done, first by John Clauser in 1974, later by Alain Aspect in 1982, and last Thursday by Henning Weyer at Q-tools in real time. And in all those cases, we find, in fact, that at the bottom here shows the results for averaging W times Y prime is 0.7, averaging W times Z prime is 0.7, averaging X times Y prime is 0.7, and averaging X times Z prime is minus 0.7. So when you combine those with a plus plus minus combination, as Bell instructed us to do, you get plus 2.8, which is greater than 2. And remember, we have millions of measurements here, and therefore this measurement is well within the margin of error. In fact, the chances that this result exceeds 2 just by accident is like 1 part in a billion or 100 billion. So that's not the case. It really is exceeded 2 significantly. So then I put in this quote here from Alice in Wonderland. Alain Aspect says, "This is curiouser and curiouser." And I explained earlier that John Clauser did the experiment because he was hoping this number would be less than 2 always, and we could hold on to our classical intuition. This is why it's considered to be very curious, because we cannot hold on to our classical intuition any longer. And just 3 years ago, there were even better experiments done where they closed all the loopholes, like the detector efficiency loophole, the speed of light loophole. The most difficult one was to close the measurement independence loophole. But let's do this poll question here. Okay, what does this really tell us? Okay, we have a spread of answers here. That's interesting. It's interesting because we need to think about the logic of how we arrived at this claim. The logic was, in those blue boxes earlier, I said that if you accept all three premises or axioms of locality and realism and measurement independence, if you accept all three of those together, then you can prove that Q should be less than 2. Therefore, if you observe Q greater than 2, the only thing you can say is that the combination of all three of these premises is not valid. See the logic? But it does not tell you which one of these three has to be considered not valid. It only tells you the combination. Therefore, we're in a sticky situation because we can't come up with any conclusion that we might like to, which is that we can throw out locality, like maybe there's wormholes, or we can throw out realism, or we can throw out measurement independence. We have to throw out at least one of these, or two of them, or all three of them, but we don't know which ones it is. Now, this is really philosophy, in a sense, at least at the current state of physics. In the future, if we could do new experiments and figure out which of these to throw out, then it would elevate this whole discussion to physics. But until we can do that, we're not quite sure what to say about it. So there's, millions of words have been written about this, but we don't know what the answer is. So strictly speaking, it shows the combination of all three of those cannot be held up. And to remind you, locality is also called local causality. It's the claim that no influence can travel faster than the speed of light. Therefore, distant objects cannot influence each other causally, at least over very short time periods. So the experiments were done over very short time periods, like microseconds, and the objects in the laboratories were separated by kilometers. Realism was the claim that all objects have pre-existing inherent properties or instruction sets for what observations will be obtained on measurement. And that means during the creation of the particle state, they can be anything, but once they're created with some probability and they travel out to their laboratories, at that point their instructions are built in to each object and they can't be changed. And that's how classical physics works, right? So that's a very reasonable assumption to take. And the measurement independence says that the two sides of the experiment can randomly and independently choose which measurement scheme to use for each measurement, with no outside control or tampering, or as in an election, we would call it rigging. So, but only if we assume that all three of these statements are true, can we prove that Q should be less than 2. So because Q is not less than 2 in experiments, we have to conclude that one or more of these is wrong. All right, so that's what we conclude. Yes. Okay, now the point is that even though the classical logical philosophy fails to explain the experiments, there is a theory that models these experiments perfectly, and that theory is called quantum mechanics. So it works, okay? It in some sense, it shows that even though the correlations are not, we don't think they're created by some causal effect like wormholes, where information travels faster than the speed of light. I mean, that could be true, but we just don't know that's true. So if you don't want that to be true, then you have to say, well, the correlations exist, but they're not caused by any causal effect. They're just built in to the way the universe is structured. And so some people like to call that holistic. The whole does not equal the sum of the parts. So I have this little picture here that if these two people are separated far apart, but they're still entangled by these strings, then even though they're far apart and they cannot communicate, their behavior might still be correlated. But of course, we know that correlation in quantum physics is very different than it would be in classical physics. So here I introduce now the notation. This is from the book, and we'll use this throughout today's session. An entangled state is written like this. Remember, the plus sign in quantum theory means superposition. This is one state of Alice and Bob, V and H polarization. This is another state of Alice and Bob, minus H and V. The ampersand means and, it means we're combining two separate objects into a single object. And then we have a superposition symbol that combines this state for the composite object with this state for the composite object. Now we're going to unpack this expression in great detail over the next 10 minutes. Okay, what is a composite object? So here I photoshopped a picture, which I'm going to use later to illustrate the point, that in classical physics, a state just means a description of the condition or the way it is. And here's a case, I suppose to be amusing. We have a tall person, Alice, and a short person, Bob. So the composite state would be written this way: tall Alice and short Bob. And that describes them together as a couple. So here is a zoom pole. Let me find that one. Pole 2. Launch this. We're focusing on the word composite state. What does that mean? And remember, composite state there's a distinction between superposition state and composite state. Why is that? Because a superposition state can describe a single object, like a single person. If they were quantum mechanical, they could be in a superposition of tall and short. But that's only one object. Okay, that's not what we mean by composite state. So let me end that poll and relaunch it and try that again. Okay, there's a bit of a different voting, which is good. People are thinking, but the word composite state always refers to two different objects and not just two different measurements. So in A would be one object, one quantum object that could be measured by Alice and Bob, but that's not what composite state means. That would just be two different possible measurements on the same single photon. Since B is the only one with two photons in it, that is the correct answer. It's the state, the combined state of two objects, like the combined state of two people who are considered a couple, and you describe one as tall and one as short. Okay, so that's what a composite state is. It describes the condition of two objects jointly. So let's unpack that. Here we have a single object, whatever it may be. Here's the state, could be a photon polarization, or it could be something else. I use V and H, but remember these labels could be other things like the path of an electron in an interferometer. This could be like the electron is in the lower path, and this could be the electrons in the upper path. And we can always draw these kind of state arrows when we have a qubit, namely an object that can just be in one of two states. And notice we draw these black arrows as they're perpendicular. And perpendicular means they're mutually exclusive. If the state is H, it's definitely not V. And if it's V, it's definitely not H. But a superposition is when we have a single object and we draw the arrow at 45 degrees. And so this would be a depolarization. And we can also represent that by a little arrow in the diagonal direction. So I'll use all these different notations throughout the session here. Now, a composite object, we have two objects, Alice's object and Bob's object. And we represent the joint state or the composite state with an ampersand. So here, Alice's photon is D, Bob's photon is H. So we can write down here D, Alice, and H for Bob, or we can write it as this little picture. Okay, so that's how we go from one object to two objects. Now you could also go to three objects. Now you'd have three of these pictures, but I'm not going to do that in this session. It gets complicated. We generally, well, until we get to quantum computing, then we will have to have multiple objects. But right now we just have two objects. Okay, and the ampersand means and. Now, both A and B can be measured separately. If one photon goes to Alice and one photon goes to Bob, they can be measured separately. But if both are measured, we call it a composite measurement. And that's exactly what we needed to do for the Bell test experiments. Okay, now here's a Jamboard. This shows two possible composite states. This up here is one composite state. I see a chat question. This is the vertical horizontal state, and this is the horizontal vertical state. This is one state, and up here is one other state. So let me check out what the chat question is.
I just sent the
Chat
link in the
question
chat.
just tells you the Jamboard. It's not a question, but go into the chat window and click on the Jamboard window, the link to the Jamboard, and we'll all be there. Oh, so let me put it this way. Just give me one. Just give me one. Right? One state, because I want to make it clear. If you could write just one state that is mutually exclusive to both of these states. So none of these answers so far are correct. So just give me one state. Okay, this state is, I'm going to call this V and H. This state is H and V. Give me one more state that is mutually exclusive to both of these states. And you can't use a slash, because a slash, like V slash H, that specifies a measurement scheme. You have to use ampersand, or in this case, write and. So this is H and V. Okay, so now we're getting somewhere. D is not correct. It has to be able to form something and something. And it's not D and A. Why not? Because we know that D is not mutually exclusive. Here I'm going to draw a D, okay? D is not mutually exclusive with H. And it also is not mutually exclusive with V. So it cannot be D and A. And this one is not correct because the notation is wrong. So it cannot be D. And it cannot be none. There are two more states, but just think of one state. So think of it classically. If I had these two people, and one was tall and one was short, what are the four possible combinations of those four people? There's tall and short, tall and short, there's short and tall, and the other two combinations are obvious. Okay, now I'm seeing some check marks in agreement. They're just, in some way, they're just the classical, mutually exclusive possibilities. Any more check marks? Okay. I see a disappearing check mark. Good. And I also see this one here, which is good. Okay, that's absolutely correct. So the answer is, just like we said here, it could be V and V, which we could draw like this, V and V. Okay, that's a possibility. And then it also could be H and H, which I'll draw like that. I'll put an ampersand in there. Yeah. So those are the four possible states, which are all mutually exclusive. Because classically, if you have one, you couldn't have the other. And in quantum mechanics, you can't have any states there that could be represented by a superposition of the other states, because then they wouldn't be mutually exclusive. Okay, so we'll get back to this, but right now I'm going to go back to the keynote, which I hope you can now see on my shared screen that we're back onto the keynote. If that's not the case, let me know. Well, okay, there they are. Is that right? Yep. Yep, here's the HH. Here's the VV. Here's the VH. And here's the HV. So it's interesting, we now have four possible combinations because there's two objects, right? That's the same as it would be in classical physics. For example, if you had qubits, you could say in qubits, I can have 0, 0, I can have 0, 1, I can have 1, 0, I can have 1, 1. That's classically four mutually exclusive combinations of two bits. And in quantum physics, we represent those four combinations by these four different states. If we're using photons, but if we're using electrons, we could represent them by, say, the positions, or I should say the locations in their path, upper path, lower path in an interferometer, or we could use electron spin, and we have this clockwise. Remember, we have clockwise and counterclockwise. Oops, clockwise, counterclockwise, etc. We can have those four possible combinations of clockwise and counterclockwise spinning. Clear drawings. Okay, great. So I need to go back to here, go to there. Okay, so this is the simpler way to draw those pictures, right? Here's HH, here's V and V. Well, here's H and H, here's V and V, etc. We have these four possible states which are mutually exclusive. Or we can write them this way, these four states, this way: V, Alice, and H, Bob, and so on. Now let's just review what we just said, okay? Because this is such an important point. I want you to get the terminology correct. So this is an easy question. It's just a terminology question. So this is poll number 3. And here's poll number 3. Which of these, which pairs of these four states are mutually exclusive? So it turns out there's a spread of answers here. Okay. So it's good that I asked this question, even though in some sense it's simple because it just reviews what I just said earlier. And it's very important, especially when you're in a virtual environment like this, to make sure everybody's on the same page with the terminology before we go forward. So I'm going to discuss this a little bit more. So if you think of this again as tall, short, tall, tall, short, 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 tall, each of these boxes represents a composite state. And each of these boxes is mutually exclusive with each other box. Because, if Alice is tall and Bob is short, well, and you measure that, well, that rules out the other three possibilities, right? So I'm going to stop sharing. I'm going to relaunch this poll and redo that poll. Okay, 5 seconds. 4, 3, 2, 1. We'll stop. Okay, I'll close this. So almost everybody clicked on B, which is correct. So I think everybody, or almost everybody, can see what the terminology means. That there's 4 composite states on the page here. Each one of those is mutually exclusive to the other 3. So all pairs are mutually exclusive. Now that forms the basis to describe a more general type of states. These are only 4 possible states, but you see we haven't considered superpositions. Now let's do that. But before we do that, let's think a little more deeply about how we can represent these. Now this is going to stretch your mind quite a bit, I predict. This requires a bit more abstract thinking, which is fun because that's what quantum mechanics forces us to do. So let's represent this state, which is quite a complicated drawing. Alice V and Bob H. Remember, we can represent that by V, A, and H, B. This little symbol here at the top of this arrow is a state. And remember, we said we can always represent quantum states simply by pointing to it. So think of this as a person standing there, pointing towards this state, saying, that's the state. I see Alice is tall and Bob is short, and I'm going to point over there and say, that's what the state is. Now, that person here is not pointing at this other one, H, A, and V, Bob, because that's not this state, okay? But if the state was H, V, then you would stand here in the states, this is called state space, as it says up here, composite state space. You would stand here in the state space and you would point towards this symbol and say, that's the state. So you could point towards this one, or you could point towards this one. And that's just using a single red arrow pointing towards the composite state symbol is a way to represent these 2 arrows. So let's go to the Jamboard and think about this a little more. So I have to escape here. I'll go into the chat window and go back over to the Jamboard. Here we are, chat window, Jamboard. That's where we were last time. So now let's go to this question, okay? I just showed you on the previous slide that I can represent this complicated picture by 1 red arrow pointing up towards VH. I can represent this complicated arrow by an arrow pointing towards HV. Now notice that these 2 arrows are perpendicular, okay? We're in a 2-dimensional plane here on a grid, and I can draw 2 arrows that are at right angles. They're perpendicular. And the reason we do that is because they have 0 projection onto each other, right? If I project this arrow onto the horizontal arrow, I get 0. And if I project this horizontal arrow onto the vertical axis, I get 0. But now I want to add a 3rd state into my possible list of states. That's the V and V state. Okay, so this one we call V and V. Now, how can I draw? And I think, go ahead and use the pen tool to draw a picture over here that would represent a 3rd arrow that is perpendicular to the first 2 arrows. How do I draw? Anybody agree with that picture? 3D picture. We're on the surface of a cube, right? You can draw the axis on the surface. I'm drawing a cube here to show you what a three-dimensional cube looks like. It's not a very good one. Yeah, you see the point. We can draw these arrows as coming from the corner. Here's a corner of this 3D cube. Very nice. I think I'm supposed to go to the next slide. What if I have the fourth one? What the fourth one is this and this. How do I draw that one? As a single arrow. That's at right angles. Can't draw in 4 dimensions? Why not? I think it's Google Jamboard is to blame. Google Jamboard does not have a 4-dimensional graphic application, so we can't draw that. Right. There was a movie, I think, about some group of people that were trapped in a 4-dimensional cube and they had to escape it. Anybody remember the name of a 4-dimensional cube in mathematics? What's a 4-dimensional cube? It's called, I might be misspelling this, but it's called a tesseract. And you can Google tesseract on YouTube, look on YouTube, you can see really cool movies trying to illustrate what a tesseract is. So yeah, that's the problem. We need to have a 4-dimensional cube, but then we need to draw these arrows along the surfaces or the edges of this 4-dimensional cube. So a mathematician would have no problem with this. They would just say, well, don't draw it. Come on, just write down the formal expression. And you're fine because you have 4-dimensional space. Now, it points out that this is not real space because our real space is 3-dimensional, at least the way we perceive it. So this, it means that this state space is 4-dimensional only because we have 2 qubits. If you had 3 qubits, the state space would be even higher dimension. And again, mathematicians have no problem with this. They just do it. Okay, so that's kind of mind stretching, but we can do it. So I'm going to go back now to the keynote and see where that takes me. Here. I'm going backwards now into what we did several weeks ago. So don't get confused because here I'm going back to a single photon. Okay, this is a single photon and it's in a state which is D. So D is equal to V plus H, which you can also draw this way, vertical arrow plus horizontal arrow. And if you want to put in the coefficients, it's 0.71 H, 0.71 V. Because remember, if you square those numbers and add them together, you have to get 1. So we did that before. So here is a Zoom poll question, number 4. Okay, 5 seconds. We're missing a few votes here. I guess that means not sure. Okay. Good. Okay, very nice. I actually like the answers that we have here, because the answers are showing some B and some C. And it turns out that both of those answers are correct. Because if I can annotate this, we know that we can have this one, which we call, this one we call D, right? This one we call A. And A is equal to V minus H, because here's minus H. So this is A. But remember, we can also have minus A. And those are actually the same state. So that this one is H minus V. So we can have the minus A as well. Good. Those are only different by phase change, but remember, in polarization, the state vector oscillates back and forth very rapidly between these two values. So if you make a measurement, they really give you the same probabilities. When you project something onto an axis, remember you project it down at right angles just onto this entire line here. And you take this point here and you project it down the shortest possible path onto the perpendicular line. And that line contains both A and minus A. Okay, clear those drawings. Go back to the mouse, close that. So this just summarizes one of the possible answers, the A one. So A is this arrow pointing off to the left, like that, and it's a V plus minus the H. So we put a phase shift in here. And you can write it this way, minus H, or you can write the arrow and then say there's a phase shift on the arrow, which would flip the arrow to the other direction. And notice that if I have this state, this is D, and that's V plus H. If I have this other state, which is A, that's V plus minus H. These have the same probabilities for H and V, but they're mutually orthogonal states. That's because they're perpendicular to each other in this state space drawing. And mathematically, they're only different by a phase shift between the V and the H, minus phase or plus phase. So that's the way quantum arithmetic works. So now let's consider superposition of composite states. This is now a new abstract leap, a quantum leap. This wouldn't apply to people, but it could apply to electrons, right? You have this state, which is a possible state, short and tall. Now this state, which is tall and short. Now we agreed earlier, those are mutually exclusive, but we can always make a superposition in quantum physics between two mutually exclusive states. So taking a slice out of our four-dimensional state space that we contemplated in the Jamboard, here's a two-dimensional slice out of that four-dimensional space. And I've indicated the tall and short state by this black arrow, the short and tall state by this black arrow, and the composite state, because there's a plus sign here, by this arrow that's halfway in between them. Now, what would this mean? Not for people, it's impossible, but for electrons or photons, what would that mean? Well, it means there's a correlation. If you see one, you know the other. So let's say you just saw, this short person here walking through the door, and you hadn't seen the other person yet. Just by seeing the one person, if you know that this is the state, you could correctly predict that the other person is tall. But if you saw the first person as tall, then you could correctly predict the second person was short. So that's a correlation. All right. So the flaming statement is that in quantum physics, superposing any two states always gives a new state, which is a possible state that could be made in the world. Now that's kind of like a cat is dead and alive, right? The dead state plus the alive state. Well, of course, that's silly because it doesn't apply to cats. So the whole Schrodinger cat thing is kind of silly. But it does apply to electrons and photons. So here's the example for photons. This is one possible state of the composite pair. This is another possible state of the composite pair. And this is a superposition with a plus sign. This is an entangled state. So now I think you've seen in detail what we mean by entangled state. And the interesting point is that there is no unique arrow, state arrow for Bob's photon alone, right? Bob's photon could be H or Bob's photon could be V. But notice we also cannot write this as Bob's photon is D. So that you might be tempted to say, well, it looks like Bob's photon is H plus V. Therefore, you might be tempted to write that Bob's state was D, which would look like this. Would look like Bob's state is actually D. But that's not true, because if I said Bob's state is D, well, what's going on with Alice's state? Alice's state could still be V or H. But it's not the case. You might say, well, let's just make them both D. Okay, let's say we have D and D. Let's say we think that's the right way to state it. You see, now we wouldn't need a superposition. Is that valid? No, that's not the same state as the one I've shown here. So what I posed was, could this state that's shown up here be represented by D and D? If that were the case, we would write D and D, and this D for Alice's photon, Alice, would be H plus V, and Bob's photon would be H plus V as well. So now we would see there's a combination of V and H. That is this one here, actually is this one, V and H. And over here we see a combination of H and V. So that would be this one, H and V. So that would be okay. But notice, this state that I wrote here also contains HH. It also contains VV. You can see it there, H, H. So what's up with that? That does not exist in this state. So what that proves is that I cannot write this state as D and D, or I cannot write this state as some state of Alice and some state of Bob. That's mathematically impossible. So the point of all that is that you cannot think of this state as being D for Bob and A for Alice, or D for Bob and D for Alice or something. This is truly an entangled state, which cannot be written as Alice's state and Bob's state. That's the nature of entanglement. Now, if this thing will allow me, I'll go to the chat window and see if we have some questions here. Right. The question is, composite states make me think that we're creating inherent properties for the system, in the sense that since if we know one part of the system, we immediately know the other part. That's a very good observation, but it's not correct. I've only been using these classical examples so you can understand what it would be in a classical physics situation. But notice, here's the difference. For the tall, short people, I was only given examples for one property, namely height. And so if you only measure one property, you can use a classical model which uses the idea of inherent properties, so tall and short. So in the example that I've written here, well, how should I say? I'm going to get rid of all these drawings here. And we're going to get rid of this, get rid of this, get rid of this. Okay, so if I just had this composite state on the left, and then I had a superposition with this composite state on the right, and if I only measured in the HV basis, then I could use an inherent properties description. You see, because if I'm just measuring HV, then if I were to measure Bob H, then I would know that Alice was V. But if I measured Bob V, I would know Alice was H. So it looks like inherent properties, like tall and short. But now here is the punchline. What if you measure this same state in the dA basis? See, now you need the quantum arithmetic to tell you what the correlations are going to be. And it turns out that's how you violate the Bell inequality. That's what Henning did. And when you violate the Bell inequality using the entangled state, like this one, you prove that inherent properties cannot possibly model that situation. Okay. Okay. Very good. All right, so moving along, what if I put a phase shift in here? So this little green minus sign is the same state I had before, as you can see here. Now I'm just going to add a minus sign right there, if I can get it to go. Bing. So I didn't change the two mutually exclusive possibilities, this one and this one. I just added a minus sign here, minus sign. So it looks very much like this same state. And notice that if I were to measure everything in the HV basis, I'd have the same probabilities because the minus sign squared would just give you +1. So I'd still have half a chance to get this combination or half a chance to get this combination. But now, as we said on previous slides, this state here with the phase shift is mutually exclusive to this state here without the phase shift. So you can see there's something very different going on in quantum physics than in classical physics. And in particular, if I were to now measure this state in the dA basis on Alice's side and the dA basis in Bob's side, you know, I'd have to go through my quantum mathematics, and it would actually depend, my probabilities for Alice and Bob measurements would depend on whether I had a phase shift here or not a phase shift. So this is certainly not classical probability theory, and it does not represent inherent properties. And here I illustrate that by graphically what I just said. Here is the composite entangled state with the plus sign here. And I can represent that by a diagonal arrow. This is in 4-dimensional state space, but I've only taken a slice in 2 dimensions out of that 4 dimensions. And I can have the same state with a minus sign here, and that would be an arrow going this way, minus 45 degrees. So it's at a right angle to this, this one up here. So they're mutually exclusive still. But again, if I measure that in the HV basis, I really can't distinguish classical probability from quantum probability. That's why Henning had his polarizers on little motors, remember? He had little pieces of tape stuck onto the edges of his polarizer rotators, and the computer was cycling through different combinations of polarization angles. And by cycling through those different angles, he was able to get statistics, which proves that the simple inherent properties model doesn't work. So I know this is a lot to absorb, and I don't expect everybody to understand the mathematics, immediately, but I think you get the gist of it. Let's do poll number 5 to see if you get the gist of it. So remember, in this case, it's kind of like the classical correlations with the inherent properties, because Alice and Bob are both measuring in the HV scheme. And the state is defined in terms of two mutually orthogonal possibilities in the HV scheme. The state is defined in the same scheme that the measurements are made in. So this makes it look more classical. So people are moving slowly on this, so I'm going to end this poll and I'm going to relaunch it. So this one kind of mimics the classical statistics. Okay, so not everybody was brave enough to put an answer in, but those who did put an answer in said A, H, and that was correct, because this is just like classical. If Bob sees V, Alice is going to see H, because this other possibility is simply ruled out. This possibility is ruled out by Bob's initial measurement of V, which forces the conclusion. Notice that I said it forces the conclusion. It doesn't change Alice's photon. This is a very subtle point. It's not that Alice's photon previously was V and it suddenly switched to H or something. These possibilities describe holistic properties of the pair. And so it's not that Alice's photon suddenly changed its state. Well, how should I say? It did suddenly forget what its original state was, because earlier it could have been V or H. But it was entangled so much with Bob that all you can say is that when Bob sees V, then Bob can conclude that if Alice measures in the HV basis, she will see H. It's a logical conclusion based on information theory. It's not that Bob's measurement somehow physically changes Alice's measurement, because we know that these two laboratories could be 1,000 miles apart and the measurements could all be made very, very quickly. So there's no causal effect here. Many popular media say this wrong. They say that Bob measuring V affects Alice's photon. And that's simply not true. Why do we know it's not true? Because we know that according to quantum mechanics, Bob cannot use this method to send information or a message. Bob cannot send a message, so therefore that means there's no physical influence of Bob's result onto Alice's photon. Okay, now here, this is maybe our last slide before the coffee break. This one's a little more tricky because the state is defined in the VH scheme, but now Bob measures in the HV scheme and gets V, but now Alice decides to measure her photon in the A scheme. Okay, fantastic. We have 5 answers in 30 seconds. That's a record. In 30 seconds, we got 5 correct answers to actually a very hard question. So congratulations, it's fantastic. C, because just like before, when Bob measured V, and we're thinking we're Bob, okay, we're Bob and we're gonna try to predict what Alice is gonna see. I see a chat question coming up. So if Bob observes V, it allows him to rule out this entire other possibility for the composite state. So therefore Bob knows up here, he saw V, so this is ruled out. So if Bob sees V, he knows that Alice's photon is in the H state. That doesn't mean it's H polarized, right? That would be a classical way of saying it. He knows that Alice's photon is in the H state. But since Alice is measuring in the DA scheme, she tells Bob, yeah, I'm going to do that. He says, oh, now I can predict that Alice is going to see 50% chance of D or 50% chance of A, anti-diagonal. So that's exactly correct. So let me see what the chat question is. Progress. Excellent. That's right. So we're going to take a coffee break soon here. So we'll take the break now, but let me just tell you what we're going to think about. We're going to first think about this simple question here, a simple setup. This is not the Bell test experiment, but it's the precursor to it. So if Alice and Bob both use calcites in the HV scheme, then Alice measures just one variable called W. And it would be -1 if she sees, if this detector clicks, and +1 if this detector clicks. And Bob just uses one scheme. This is like the first phase of an experiment, right? They both use the same scheme. And Bob calls his observed variable Y, which can be ±1. So what we're going to try to figure out is what would happen if the source produced this state right here, V on Alice's side and V prime on Bob's side. So that's the state where the state arrow is at -22.5 degrees from V. Now here's an ampersand, that means and. So this is a composite state, but let me ask you really quickly to think, is this an entangled state? The answer is, aha. Think again. Is this an entangled state? I can write this state here as a product of Alice's state and Bob's state. And I said earlier that anytime you can write it as simply a product where Alice has a definite state and Bob has a definite state, that's not an entangled state. An entangled state would be I have like this composite state plus another composite state over here that was different than this one. If the composite state can be written as a state of the A object and the state of the B object, then these are two definite states, one for the A object, one for the B object, then this is not entangled. Okay, what you need is to add to that, possibly with a minus sign or a plus sign, a different state for the A object and a different state for the B object. And typically when you write it this way, if it can, it's entangled, but you need to check to make sure that you can't simply write that in some more tricky way, like some third kind of state for the A object and some third kind of state for the B object. So this is a hard mathematical problem, but you need to, if you see something like this, you need to make sure you cannot do a trick and rewrite it as a product of two states. Okay. So this is a bit more advanced concepts here, but that's what you need to understand for entangled states. And so we were talking about this example here as a supposedly a very simple example. And the reason it's simple is because we're just measuring in one scheme, namely the HV scheme. And notice that Alice's state is, it's in a definite state relative to the HV measurement. So if you want to use the word eigenstate, which I have not used before, Alice's state is an eigenstate of this measurement scheme, because anytime this photon comes into here, it's always going to go to the -1 detector, because the state is V. Okay, but Bob's photon over here is in the V prime state, which is a superposition of H and V. So sometimes his detector is going to click minus, and sometimes it's going to detect as the plus. And what we're going to do is be able to predict the correlations here. Okay, so here is, we're going to go to the Jamboard, but let me set it up for you first here. How to write this state as a sum of two states using only H and V states, because that's what Alice and Bob measure. So the point is that when you write a state to make predictions, you need to write the state or express the state in terms of the same schemes that Alice and Bob are going to use to make measurements. So here we have the state that I posited was produced by the source. Somehow we made the state. So there's V for Alice. But now Bob's state is V prime. And remember, we have all these different definitions down there. Here's the V prime state. It's tilted minus 22.5 degrees from the vertical axis here. And we can write it as shown in this red underline equation. It's minus h times 0.38. That's this little segment here. And then this vertical segment is 0.92 duration length. And remember, if I square this number and square this number and add the two together, I have to get 1 because those squares are the probabilities. Okay, so given that that is the way the state is represented, here's the V prime state. It's represented like this. And now let's go to the Jamboard. I will go to the chat window, click on the Jamboard link. And I'm there. Page 4 of the Jamboard is this question. And there's yellow boxes and yellow circles, which you're supposed to fill in. And you can write the answers outside of the box because there's only one page here and there's many of you. And I will remind you which equation is the important one. This one here. Now there's something you have to figure out here. It's not obvious until you see it. It's not a trick, but it simplifies things. I'll give you a hint. Notice that Alice's state is V, and it's always V. It's V on all three boxes. So what I said was using only the H and V states. So this little arrow that was just drawn, I'm going to erase it. Sorry, trying to be efficient here. You have to draw inside the circles only this or this or this or this. Those are the possible H and V states, because notice that down here, I've only used the H and V states to represent everything, because we want to know what's the probability that Bob's going to get H if he measures an HV basis. Okay, that's looking good. I see this one. And I see this one. Now we need the numbers also. These numbers have to fill in the square boxes with numbers, not just plus or minuses. We got the 0.38 and the 0.92. So yeah, we've got V minus H. Okay. Yes, those are correct. Super. And the way you can see that once you see it is because Alice's state is the same, I could just stick that out here and say Alice is V, and then I could just cross it out from here, here, and here. And now we're just decomposing Bob's state, or we're re-expressing Bob's state. So V prime is equal to 0.92 V minus 0.38 H. Actually, little correction here. If you drew the arrow this way, that is the minus H. If you draw the arrow this way, then these have to be plus, because you don't want to put the minus sign in twice. The alternative would be minus 0.38 and then draw the arrow this way. That's equivalent to plus 0.38 here and the arrow drawn to the left, because that's the minus H state. Okay. So, these are important mathematical details if you want to do an actual calculation, but I'm sure you're getting the idea here. Now, I made this example simple so you could do it, because now we can just separate the Alice state here from the Bob state and treat the Bob state. That's because it's not entangled. Yay, see, it's not entangled. See, that satisfies my rule. If I can write the state as the state of Alice over here, and then times the state of Bob, it's not entangled. So we can deal with the Bob's state separately. All right, fantastic. Let's, I can't remember what is on the next page. That's for later. Okay, let's go back to Keynote. And yeah, there it is. I put the order differently than what was on Jamboard, but 0.38 minus H, that's this one, and then 0.92 plus V, that's this one. Given this state, what's the probability that both Alice and Bob will observe V? I'll let you think about that since I don't have a Zoom poll for that. Well, so the answer is, I'll write on here, the answer is the probability for V and V, remember that's our symbol for joint probability, comma, is 0.92 squared. Because that's it. This is the component of the composite state in which they're both V. Okay, so that's before anybody makes a measurement, you can make that probability prediction. And you can repeat the experiment 1,000 times and you'll get that answer. But now, here's a different question. Conditional probability. Conditional probability. What is the probability that Alice will observe V given that Bob observed V? Remember that says given. So let's say Bob measures V, and then he's going to make a prediction. Given that I just observed V, what is the probability that Alice will also observe V? Well, actually, it's always 1 because everything is V, but the point is that it's no longer 0.92, it's now 1. You see, because now this state has been ruled out by Bob's observation. So this gets replaced by a 1. So that's interesting. If Bob calculates the probabilities before anybody makes a measurement, the probability of V and V is 0.92 squared. But if Bob goes ahead and he does see V, then he can predict that Alice will also see V with 100% probability. Girl drives. Okay. So, right. I say Alice's state comes along for the ride. Which means it's not an entangled state. So let's talk about the Bell state, all right? We haven't shown the Bell state yet. Well, I think maybe earlier I did. Let's show it again. So here's a state which is not the, no, this is the Bell state because there's a minus H right here. So we have VH plus minus HV, and they occur with equal probabilities, namely 0.71 squared, 0.71 squared. That's the state that Henning made in the laboratory last session. So again, probability is 0.5 because that's 0.71 squared, probability is 0.5. And notice this arrow points to the left, that's the minus H. Okay, recall these relations for D and A, and D prime, which is this minus 22.5 state, and this A prime, which is this minus 67.5 state. Okay. So now there's a lot of mathematics. So you can you can check your email or your social media feed if you want. But I'm going to go through this real quickly, and I don't expect you to follow the details. But if you're really curious, you can look at these slides later and verify and see if I've made any mistakes. So here's the state at the top that we just looked at. Okay, this is the Bell state. 0.71 VH plus minus 0.71 HV. Notice this time I put the minus sign outside here and I use the plus going arrow. Okay, now the hard part is we know that we need to represent or adapt the state description to what will be measured. So let's consider a particular measurement scheme. Alice will measure H and V, and Bob will measure H prime, V prime. And that was one of the 4 combinations that Henning used in his experiment. Okay, so let's fix the measurement schemes to be that. Here, Alice is going to fix on HV, Bob's going to fix on H prime, V prime, and then they're going to run 1,000 trials. Now, given those settings, there's 4 possible combinations of measurements they can get, right? Alice could get V and Bob could get H prime. That occurs with a probability 0.65 squared. Because I did the math for you, just don't worry about it. Or Alice could observe V and Bob could observe V prime. That occurs with a probability of 0.27 squared. Or Alice could observe H and Bob could observe H prime. That's probability 0.27 squared. Or Alice could observe H and Bob could observe V prime, 0.65 squared. Okay, so notice that Bob can only observe H prime or V prime, H prime or V prime, and Alice can only observe H or V or H, V or H, because they have fixed their measurement schemes, so they only each have 2 possible outcomes, but there's 4 combinations, right? And of course, later we're going to go on and do the other 3 measurement schemes, but we're just doing the first measurement scheme right now. So let's look at it. Here's the probabilities that I just told you about. They all sum to 1. That's good. Calculate the average of Alice's observable, of Alice's quantity W times Bob's quantity Y prime. W can be plus or minus 1. Y prime can be plus or minus 1. So as before, we have the plus 1, the minus 1, the minus 1, and the plus 1. Those are the products. And we have these probabilities, the blue numbers, the probabilities. So we do the math, we get 0.07, which is just what I told you that Clauser and Aspey observed in their actual polarization experiment. And it's pretty close to what Henning observed too, but he didn't show us that number. Okay, so that's one of the 4 settings. Now Henning has to rotate his polarizers to one of the other 4 combinations and then make the measurement. And then he has to do it again, and then he has to do it again. So when he does it, he goes WZ prime, he gets 0.7. When he does X, Y prime, he gets 0.7. Again, using the same mathematics as here for each of these cases. But the last one is H times Z prime, and that's minus 0.7. So there you have it. Q is 2.8, because it's this number plus this number plus this number minus a minus number gives you plus this number. And Henning, when he did the experiment, he got 2.5, which is pretty good. It's greater than 2 within the margin of error. Some people have done this experiment with more expensive apparatus, and they actually got 2.8, very close to 2.8. So the fact that this is greater than 2 means we have violated the Bell inequalities, and it's proves some kind of global or non-local correlations. So the point is that this proves what I just showed, is that the theory of entangled states predicts exactly the correlations that are observed in the experiment. But it really has nothing to do with those 3 assumptions about locality, measurement independence, and realism. In other words, quantum mechanics doesn't make any assumptions about those 3 premises or axioms. Quantum mechanics is a purely mathematical abstract framework, which I just walked you through, for predicting correlations. In some sense, that's all it is. It's a model. It's a mathematical structure that people have invented to allow them to make predictions. It doesn't tell you anything about what's going on underneath or behind the curtains, as they say in the Wizard of Oz movie. But it works perfectly. So yeah, use it. I'm going to use it to do really cool things like quantum teleportation and build quantum computers. So here I've mocked up a keyboard with your standard symbols: diagonal, psi, greater than, less than, anti-diagonal. So this is my humorous attempt to make a quantum keyboard. And of course, you can nowadays, you can get access to a quantum computer that's operated by IBM, and you can actually program your own quantum algorithms and run them on the IBM computer. It's a very simple computer with very few qubits in it. But if you're a company or a university and you pay thousands of dollars, you can get access to a much larger quantum computer with maybe 25 qubits or something. Okay, so time is short, and I don't want to confuse your thinking too much with a new topic, because I want you to digest what we just went through during the last hour and a half. So if you have time, I'd like you to download this, these slides from the Google Drive and go through everything we did and try to verify what we did. So I'm not going to go much further here. I'm just going to introduce the concept qualitatively. And then next lecture, we'll discuss this in detail. That'll be our final session. So the point is that in a computer, you need bits and you need logic devices. So typical kind of logic device is one that takes in 2 different bits, has 2 different values. We could call one of them Alice's bit and one Bob's bit. And they have a state. This could either be a quantum state or a classical state. Here I showed it by 2 coins, okay? So the coin can be heads or tails. So here H means heads, T means tails. The rule for this device, which is a simple logic rule, which is called SNOT, by the way. Here's the rule. You have to build, well, IBM builds this little device for you, They give you qubits. You can specify that each bit is either H or T. Throw it into this device and see what comes out. That's one logical operation. Or in computer terminology, that might be a flop. So here's the way this device works. If Bob's coin is H, then Alice's coin state is unchanged. Okay, so the value of Bob's coin controls what happens in the device to Alice's coin. So Bob's coin is called the control bit. Okay. If Bob's coin is T, then the device does an operation where it flips the state of Alice's coin. So if it was originally heads, it would now be tails. If it was originally tails, it would now be heads. And in either case, Bob's coin goes through unchanging. So it's very simple once you get the picture. Bob's coin goes through without changing. If Bob's coin is T, then it causes the device to flip Alice's coin. But if Bob's coin is H, then Alice's state is not flipped. Now, in classical computers, if you studied that a little bit, you know that typically you put 2 bits in and you just get 1 bit out. You just get the A bit out and the B bit is thrown away. In quantum computer, you have to have both bits coming out. Why? Remember, later we're going to take these bits and we're going to do more things to them. But the more fundamental reason is this device has to be a quantum mechanical operation. And remember when we talked about paths of photons or electrons going through interferometers? We only had 1 electron or 1 photon, but the point is still the same, that the operation has to be unitary. And unitary means that it's obeying quantum mechanical rules. The device is closed and sealed. You cannot look inside there to see what happens. And in fact, you cannot even look out here to see what happens. You're not allowed to look here. It's covered up. This whole thing's in a box. You can't look in there. If you look in there, we know that that's going to convert the quantum state into a classical state. And the particles will forget their earlier quantum state. Don't want that to happen. So you need this whole device to be unitary, which means you cannot block one of these paths. Because if you block one of the paths, it's not unitary. So that's the basic device. You build the quantum version of this, where you can now put in qubits into here and here, and it's unitary, and some composite state goes in, whatever it is. This could be a superposition state, and this could be a superposition state. So this could be now an entangled state. And then the device processes this combination of 2 qubits in a unitary manner. Both qubits come out, and now they're in a different state. It turns out that this is all you need to build a quantum computer. If you can do this, and then have many of these qubits, like 35 qubits and 35 devices, and then whatever the outputs are coming out here, you can cross them over and combine them in different configurations and run it through more devices. You can build any quantum algorithm that you want. There's one small caveat, which I'll explain next time. But basically, this is the whole game of quantum computing construction. You have to build this device. You have to keep it unitary. You cannot let decoherence come in and change the phases of the states, because remember, when you have a composite state, which is entangled, and if you just get a small phase change on one of the states, it changes the state. So that would be decoherence. You cannot allow that to happen. And this is why it's so hard to build a quantum computer. You have to build many of these devices. They always have to transmit both particles out without being detected in any manner. And then you have to be able to repeat that hundreds of times without having decoherence. That's all you need to do. And then at the end, you need to measure them. But measuring is not difficult because you just measure in some eigenstates at the end. So this is all you need to build a quantum computer, and you might wonder why it takes 30 years and billions of dollars to build one. It looks pretty simple. We'll talk about a little bit more about that next time.